Chapter 12 coming at you. We got sequences and series. Oh, it's going to be fantastic. Those of you that very much enjoy pattern recognition, this is going to be the chapter for you. I'll tell you what. Alrighty, so when you hear the word sequence, think of a sequence of events, okay? So when we're dealing with this in mathematics, it's like the first, second, third, fourth, so on and so forth terms, okay? Cool. Apparently, I need to update my virus software. All right, so a sequence is a function whose domain is positive integers. Positive integers. Cool. And what we mean by that is you're going to be going like term 1, term 2, term 3, term 4, so on and so forth. So the 1, 2, 3, 4, the term number, that would be your input, your domain. So let's take a look at example 1 here. We want to write the first several terms of a sequence. All right, so we have this n squared over 2n plus 1. All right, so if I put a 1 in, so if you notice a sub 1, that means I'm just going to be substituting a 1 in for n. 1 squared is 1, and then 2 times 1 is 2, plus 1 is 3. And then if I plug in a 2, so a sub 2, that means I'm doing 2 for n. So I'd have 2 squared is 4, and then 2 times 2 is 4, plus 1 is 5. Not too bad, right? Go on to 3. I'd get 9 divided by, let's see here, 6 plus 1 is 7. And I figure I'll just fill in the rest of them there to save a little bit of time. I think you can plug numbers in and simplify if necessary. These didn't simplify. All right, so there we go. First example done, right? Not too bad. One thing, if you are going through any of the PDF notes, there are links. There's author and action videos. So if you don't particularly like my video or you just need a little bit more, there you go. Anything that has a star means they have a video for that. All righty. Cool. So again, we're going to write down the first 6 terms of the following sequence. Feel free to try it, pause the video, and then see if you've got it right. Cool. All right. So for my first one, if I plug a 1 in, -1 to the first power is -1. And then 2 times 1 is 2. So 2 times -1 is -2. Cool. All right. Now if I plug in 2 for n, now I'm squaring that -1. So it becomes +1. 1 times 2 is +4. Okay? These are the term numbers. I don't want you to think that those are fractions, so maybe I'll get rid of those. All right, now if I plug in 3 for the third term, -1 cubed is -1. 2 times 3 is 6, so -6. And then 8, -10, and 12. 12, +12. Okay, cool. So again, writing down those first terms, we're just plugging in 1, 2, 3, 4, 5, 6, so on and so forth. Not too bad. Now, this one's a little weird. Example 3. Write the first 6 terms of the following sequence. We got n squared if it's even, and n if it's odd. So like restrictions on each one. So let's see here. If I plug 1 in, that's an odd number, right? It's n, which would be 1. Now, if it's even, which is the second term, 2. 2 squared is 4. And then the third term, it's odd, so it plugs in for n, which would just be 3. And the fourth term, 4 squared is 16. And then the fifth term, it's odd, so it's just n. And then the sixth term, squared, is 36. Cool. All right. So kind of a weird one there, but, just following the directions and the restrictions on there. All right. Let's see here. Ooh. Write the first several terms of a sequence. Determine a sequence from a pattern. So we're given the first several terms. Now we're going to write the formula, right? Cool. Now I find it very helpful in these to jot down what term number it is. So 1, 2, 3, 4, because that's what's going in for n. And then I can think, okay, well, how would I get that, right? Let's see here. I got 1, 2, 3, 4. If I look at the numerator doesn't change. So I'm thinking it's going to be something like this, 1 divided by something, right? The numerator stays 1. The denominator is going 2, 4, 8, 16. That's 2 getting to the first power, then 2 squared, then 2 to the third, then 2 to the fourth. I think we've got it. 2 to the n. All righty. Had to pause for the music. Ooh, voice crack. All right. Next one. We've got, let's see here. Go 1, 2, 3, 4, so on and so forth. So That's what my n is going to equal, right? It's the term number. So it's just alternating between negative and positive. If I were to raise -1 to an odd number, it would stay -1. If I were to raise it to an even number, it would become +1. So what I'm getting at here is that we're going to have a sub n is equal to -1 in parentheses raised to the nth power. If I raise it to the first, I get a -1. If I raise it to the second, it becomes +1. So on and so forth, back and forth. So when you have change in sign like that, start thinking of a negative number in parentheses being raised to the nth power, because the alternating odd and even will change it between negative and positive, right? Okay, letter B here. It's going up by 2 each time, right? So if we go from 1 to 2 to 3 to 4, it's going up 2. So +2, +2, +2, right? Okay. So each one is going up 2. Decided to change how I wrote it. I felt like the numbers were getting a little bit in the way. Okay, so we're adding 2 each time. So if I started with 3 and added 2, I would get 5. And then if I added 2 again, I'd get 7. And then if I added 2 again, I'd get 9. So if I started with 3, so like my initial term, and then I have 2 times whatever n is, I'm adding 2, then I'm adding 2 more, so I'm adding 4, then I'm adding 2 more, so I'm adding 6, then I'm adding 2 more, so I'm adding 8. Bada boom, bada bing. So if we see a common addition or subtraction, this is a linear type of equation here. So it's set up much like y equals mx plus b, where the number that I'm adding each time is like that slope in that equation, okay? So this is linear. All right, cool, awesome. Next one. So what's happening on this one here? So it's a little different. It goes up by 3, then by 5, then by 7, so on and so forth. So this is term 1, 2, 3, 4, and 5. Okay, so it goes up by 3, then 5, then 7, then 9. All right. It's all by 2, right? Now, you might be remembering when you're graphing a quadratic, there's the up 1 over 1, then up 3 over 1, then up 5 over 1, then up 7. If you remember the pattern, this is a quadratic. There's our indicator, okay? So, quadratic. So let's write our formula like that. So I'd have a sub n equals n squared plus, well, let's think about how we started this. It starts at 3. So if I plug 1 in, I'd get 1 squared is 1. How do I get 3 then? Plus 2. Let's see if this checks out. If I plug 2 in, n squared is 4. 4 plus 2 is 6. If I plug 3 in, I get 9. 9 plus 2 is 11. Bingo, bango, we got it. I like it. Awesome. I always like to check at least the first 3. We just wrote some. We went from the formula to the pattern, just writing out the first 6 terms or so. Now we went from the terms being written out to that formula. I love it. We're getting after it. All right. So there is a different way of writing these formulas. We've got the explicit version, and then we also have the recursive version. We're going to look at the recursive version here. And what that means is we're just basically going to be looking at the previous term or previous couple terms that will help us work through this sequence here. So the notation for the previous term is a sub n minus 1. That means the term before the one we're talking about, okay? And you could even have the a sub n minus 2, the one before that, all right? So let's see here. Can we identify the next numbers in the pattern? So I've got 1, 3, 9, 27. What's happening each time there? I'm multiplying by 3. I'm multiplying the previous term by 3. 27 times 3 is 81, right? So if I took the previous term, a sub n minus, actually, let me give myself a little space, a sub n minus 1, and I were to multiply the previous term by 3, I would get the next one. But I do need to state what we're starting with. So I would say where a sub 1 is equal to 1. So now what I've got is if I want the second term, okay, if I want the second term here, I would have a sub 2 equals 3 times a sub 2 minus 1. So that would mean a sub 2 is equal to 3 times a sub 1. What is a sub 1? A sub 1 is 1. So I'd have 3 times 1, which equals 3. Okay? And then if I wanted the third term, I'd plug in 3 for n. So then this would become 3, which would make this guy 2. What's a sub 2? That was 3. So now this becomes 9. So on and so forth. And we'll write those out in the next section here so you can see them in each one because I feel like I went through that a little bit fast. Let's go to part B, though. So this one, let's see here. It goes 1, 1, 2, 3, 5. Okay. Well, 1 plus 1 is 2. So I added the first two terms together to get the third. 1 plus 2 is 3. So I added the previous two together to get the next one. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. Okay. So I'm taking the previous two terms, adding them together to get the nth term. So I would say a sub n is equal to a sub n minus 2 plus a sub n minus 1, where a sub 1 is equal to 1 and a sub 2 is equal to 1. So now I would have 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, so on and so forth. This is actually called the Fibonacci sequence. Very famous. You've probably heard of it. You probably have, actually. Fibonacci. It's a fun word to say. All right. Let's now write some of these out because I feel like seeing it written out will make a little more sense with how we're writing these formulas as well. So write down the first 5 terms of the following recursively defined sequence. And I'm going to show a lot of work here. You don't always have to show all this work. So I've got a sub 1 is equal to 2. I already know that. A sub 2 is going to be equal to 4 plus a sub 2 minus 1. So that would be 4 plus a sub 1. And if a sub 1 is 2, I'd have 4 plus 2, which equals 6. All right. Next one, a sub 3. Well, that would be 4 plus a sub 3 minus 1. So that's 4 plus a sub 2. And if a sub 2 is equal to 6, I get 10. Next one. Let's go a sub 4. So that's going to be 4 plus a sub 4 minus 1. So a sub 3, which we know is 10. So I'd get 14. So I'm always taking that previous term. Let's do one more because it says the first 5. One more color. We'll go with blue. So a sub 5 is equal to 4 plus a sub 5 minus 1. So that's a sub 4. So 4 plus 14. And then I'd have 18. All right. So there's my first 5 terms. Notice in each one, I'm taking, to get a sub 2, I'm using a sub 1 in my formula. To get a sub 2, I'm using a sub 1. To get a sub 3, I'm using a sub 2. To get a sub 4, I'm using a sub 3. And to get the 5th term, I'm using the 4th term. I'm always using the one prior to it. Hence, the term recursively defined. All right. Good stuff. This is fantastic. All right. Example 6. All right. So for this one, let's see if we can write this out, maybe doing a little bit less of the really long work here because that's a lot to write out. So my first term is 5. My second term, I'm going to take that 5 and I'm going to multiply it by 2 to get 10. The third term, I'm going to take that second term and multiply it by 2 to get 20. The fourth term, I'm going to take that third term, multiply it by 2 to get 40. And then the fifth term, I'm going to take that fourth term, multiply it by 2, and get 80. I like it. So I'm always taking that previous term to get the one after, right? There we go. That should show a little bit of work here. Always taking that previous term. Boom, boom, boom. Love it. All righty. That's some good stuff right there. All right, so this one's written a little bit weird, in my opinion. Okay, but we'll deal with it. We'll deal. All right, let me get we'll go with orange. We haven't used orange yet. All right. Ooh, 5. Okay, ask for 5. So my first term is 1. My second term is 1. Yay! But my third term, look at our formula. If I want my third term, I'm not plugging in 3 for n because it says u sub n plus 2, right? So if I want u sub 3, I would need to plug in 1 for n. I'd have u sub 1 plus 2. That's going to give me the u sub 3, right? So let's think about that. So that means I'm plugging in 1 for n. So I'd have u sub 1. And again, if I plug in 1 for n, it's u sub 1 plus 1, which is u sub 2. That's how I'm going to get u sub 3. So u sub 1 is 1. U sub 2 is 1. That gives me 2. Now for u sub 4, I would be plugging in 2 for n. So I'd have u sub 2, which is 1, plus u sub 3, which is 2. 1 plus 2 is 3. And in case you were like, wait, how did we get that? I just jotted down some work over here. So we plugged in 2 for n, and then we'd have 1 plus 2. I also wrote down some the term numbers underneath there for you. Hopefully that will help. So on to our fifth one here. That would mean that I'm plugging in 3 then for n. I took away the n equals because I feel like that was a little bit confusing since we're not plugging that in for n. So that means if I want the fifth one here, I'd plug in 3 for my n value here. So I'd have u sub 3, which is 2, and then u sub 4, which is 3. So 2 plus 3 is 5. This is actually the Fibonacci sequence again, where we're taking the previous 2 terms and adding them together. And when you look at that recursive formula, okay, u sub n plus 2 is equal to u sub n plus u sub n plus 1. Well, u sub n plus 1 is the term just before u sub n plus 2. And u sub n is the term just before u sub n plus 1. Let that sink in. Okay, I've let that sink in. So to get u sub n plus 2, I'm taking the previous 2 terms and adding them together. Certain ones we can say them in words like that, and it's very helpful. I'm just going to take the previous 2 and add them together. That's what we did on this one here. Cool. Just looked a little bit different. I like it. Fantastic. All right, let's go on to 12.1, day 2. We are going to combine this all into one video. Woo! So we have ourselves some sigma notation. That's what that Greek letter is. It's sigma. Okay? Sigma. It's an S and R alphabet. It looks like a really cool jaggedy E sometimes, but it is the S in our alphabet. And we use it for summation notation. Meaning what we're going to do is we're going to take that sequence and we're going to add those terms together for whatever length of the sequence we want to do. It'll be determined in there. We'll talk about some notation. All right? So there's a few pieces to the puzzle here, if you will. We've got, this is basically an instruction to find the sum. We're going to start with the first term with the k equals 1. It will tell us which term to start with. And then we're going to end with that nth term up on top of that sigma. Okay, so we're going to start here, and then we're going to end with this one here. And in the sigma notation will be our formula, if you will. Okay? So let's go ahead and write out the sum. Cool? So if we have our first term here be 1 going in for k. So 1 over 1 plus 1, which is 2. So 1 divided by 2 plus, and then if I plug in 2, I'd have 2 divided by 2 plus 1, which is 3. So 2 divided by 3. So we're writing out like that sequence, but with addition signs in between because we're going to do the summation, right? So if I plug in 3 now, 3 divided by 4, and then the fourth term be 4 divided by 5, so on and so forth. And I'm going to put plus, and then plus n divided by n plus 1, because n is my last term, whatever that may be. Well, you'll be directed if you're going to find an actual sum there. They can be infinite, but we'll get into all that later. All right, next one. Let's write out the sum again. So I'm going to start with 0. So if I plug in 0, because it told me to start with 0, right? The other one told me to start with 1. That's my starting point, whatever that number is. I'd have, let me change colors here so they don't overlap, negative 1, right? If I plug in 0, 0 squared is 0, minus 1 is negative 1. Plug in 1, 1 squared is 1, minus 1 is 0. Then 2, that'd be 4 minus 1 is 3. Then 4, wait, sorry, I skipped 1. 3, that'd be 9 minus 1 is 8. And then so on and so forth, we'd have n squared minus 1. Cool. I like it. Good stuff. Fantastic stuff. Lovely. But now, of course, we've written them out. What are we going to do? We're going to now write it as a sum. So use summation notation. All right. Cool. So fancy E looking thing, which is actually an S in our alphabet. How wonderful is that, right? So we're going to start with term 1, which should be K equals 1. And we're going to go all the way to which term here? Well, it looks like we got 1, 2, 3, 4, 5 terms. So 5 up top. And then what's happening here? This is all the numerators are 1. All the denominators are the term number, 1, 2, 3, 4, so on and so forth. So K rather. My apologies. And then it's going to be squared. Let's see if that works, right? If I plug in 1, 1 over 1 squared, that looks right. 2, 1 over 2 squared. 3, 1 over 3 squared, so on and so forth. Lovely. We are done with that one. Okay? I don't know why I felt the need to circle it. It's the only thing there. Next one. I'll change colors because that's fun. We'll go the lighter purple. Okay. So, let's see here. Expand and evaluate. Ooh, evaluate. We're going to get an actual number here at the very end. Let's do it. So for K equals 1, I would have 3 plus 1 is 4. And then for K equals 2, I'd get 6 plus 1 is 7. And then I would have 10. And then I would have, and I can see I'm actually just going up by 3s, right? So then I'd have 13. I'd have 16. And then we're going up to 7. So 1, 2, 3, 4, 5. We got 2 more. 19, 22. So we're all the way up through there. Now, what am I going to do? I'm going to add all 7 of these together. So that would give me 91. There's my final answer. There is a way to do this on your calculator, but if we ask you to say write them out, you still need to know how to write them out. So we could ask you to write out the number of terms or whatever it might be. But if you are using your calculator, I would use my emulator, but it doesn't have this function. So if I take this, one sec. I'm huge. That's cool. All right. So if I take my calculator, okay, and if I hit the math button, right, and then if I choose 0, sorry, it's a little weird. Look at that. Oh, snap. We can type everything in. Make sure whatever the formula is, you keep it all in the parentheses. And what I mean by that is if it's like n squared, k squared, don't put k and then arrow out to put the exponent. Make sure you put everything inside of here. Otherwise, it'll evaluate what's in there and then it will square everything, right? So keep everything that is your formula inside those parentheses. Add extra parentheses if you need to, but don't arrow out, add exponents, and go outside of those parentheses at all, okay? Those parentheses, keep everything in that sum. It'll be messed up otherwise, okay? You'll probably run into that mistake at some point, but hopefully not. We'll see, though. All righty. Let's see here. All right. Sorry, I was having some kind of a glitch there, guys. I ended up skipping a part of example 2. Sorry. Back to example 2. Part B. We have 1 plus 3 plus 5 plus and then 2n minus 1. So we want to express this in summation notation. So let's see here. I've got that awesome sigma. K equals 1. And then, this is wonderful. Look at that. 2k minus 1. And we're going to go all the way. We don't know how many there are, so we're just going to put an n, right? Because it also shows us in there 2n minus 1. We're going to the nth term, whatever that may be. And let's see if this works. So I plug in 1 for k, I would get 2 minus 1 is 1. If I plug in 2 for k, I get 4 minus 1 is 3. If I plug in 3, I end up getting 6 minus 1 is 5. Wonderful, fantastic. I love it. That's it. Boom. Done. Awesome. That's the end of this video. I hope you guys had a wonderful day. All right. America, freedom, rock and roll, Costco, and, of course, Riverdog Jenny on the gram. Have a great day, guys. See ya.